Welcome to Hartman Math. This is lesson 1.8, combinations of functions, focusing on composite functions. But before we get there, just a quick reflecting back on arithmetic combinations of functions, talking about sum function, difference function, product function, and quotient function, where we just add two functions, subtract, multiply, divide, paying special attention to dividing because we know that we're not allowed to divide by zero. So there are extra domain restrictions there. Any value of x that causes you to divide by zero is removed from the domain. Other things about the domain, on these it's not really all that critical because our functions here are polynomial functions. So those are all real numbers, but they're not always necessarily going to be that. So when we're talking about sum, difference, product, quotient functions, the domain for the result is the overlap or all of the numbers that are in common to both domains. So it's the intersection of the two domains. So some of the notation that's used for the sum function, you might see parentheses f plus g of x, not times x, of x, which just means f of x plus g of x, and so on. And then remember, when we get down to the quotient function, which is f of x divided by g of x, the denominator is not allowed to be 0. Example number 3, find the product function and its domain. So this time we're not looking at polynomial functions, so we really got to pay attention to what's going on. So we're going to first look at the domain of f of x, our square root function based on our parent functions, our library of parent functions. So it starts at 0, goes to the right. And then our reciprocal function was basically everything except for 0. So something like informally x is not allowed to be 0. So now, what is the product function if we multiply these together? Is we're going to get the square root of x over x. The domain is the overlap between these. So start here, consider these, but also know x is not allowed to be 0. So if we turn the bracket into a parenthesis, that's going to be our overlapped domain. Example 4, quotient function, same f of x, different g of x. So our domain for this, we already knew that one. That was bracket 0, comma infinity. Now g of x is a bit more challenging. There's a couple ways of going about this. We could just kind of start testing it out, plugging in x's. So like, all right, could I plug in -5? I'd get a square root of a negative. I'd get an imaginary. We're talking about everything under real numbers. So no, -5 is not going to be in there, and so on. Or we could treat this as an inequality. It's not quite that simple, though. We would say 4 minus x squared has to be greater than or equal to 0. We're not allowed to take the square root of negatives under the real numbers. And then we need to factor it. It has to be factored. So it is a difference of squares, so 2 plus x, 2 minus x, greater than or equal to 0. If we then put the zeros there, the critical numbers, on a number line, we get that, and then we can test the region. So like -5, we already tested that, false. Plug in 0, 4 is greater than or equal to 0, that's true. And then what about 3? 4 minus 9 greater than or equal to 0, not true, false. So it's true here in the middle from -2 to +2. That's our domain there. Another thing we could have done, if we think of this as like y equals, if we had squared both sides, we would have gotten y is equal to the square root of 4 minus x squared. Square both sides, y squared is equal to 4 minus x squared. Add the x squared plus y squared is equal to 4, and we're talking about a circle. Now, technically, this being just the positive part of the root, it's just the top part of the circle, the semicircle. But we know the radius is 4, so if we're looking at this the radius is 2, so we're talking about the domain going from -2 to +2, just another way of looking at that. All right, so now the quotient function, that divided by that. The domain is the overlap, so starts at 0, so none of the negatives matter. Goes to infinity, except this one doesn't go to infinity, it just goes to 2. So the overlap between this set and that set starts at 0, ends at 2. Okay? But once again, can't be 2 because that's coming from the denominator. If I plug in a 2, I get divided by 0. It's not allowed to divide by 0, so we have to turn that into a parenthesis. Say, yeah, it can't be 2. Also can't be -2, but that part excluded the -2. So here's our domain. All right, so now we get to the composite functions, where essentially we're looking at f of g of x. So we're going to take a function and substitute that into a function. So the notation is f open circle g, and it's read as f composed with g, or f of g. It's not a multiplication where they forgot to fill it in. Okay. And a very confusing diagram here for figure 1.55 that says, starting with x, the x's have to be in the domain of g. That is the inner function, which we will talk about. So then we perform the g, and it takes us here. And then we perform the f, and it takes us here to f of g of x. So the definition of f of g of x, or f composed with g of x, we're going to probably want to think of it this way, and then substitute a function into a function. And the domain is the set of all x in the domain of g, such that g of x is in the domain of f. We'll talk about how we navigate that. Example number 5, find f of g of x, or f composed with g of x and its domain. We're going to start with the inner function. We need to know the domain of the inner function. That is the second one listed. So g of x is our inner function. We need to know its domain. As it is a polynomial function, linear in this case, the domain should be all real numbers from negative infinity to positive infinity. All real numbers. So we have no issues there. Then we do the composition. So we're going to go f of g of x. So our first substitution is here. Replace g of x with 3x minus 2. So it becomes f of, replace 3x minus 2. That then gets plugged in here and here. So both of the x's get replaced with 3x minus 2. 3x minus 2 squared plus 5 times 3x minus 2. Square here, meaning 3x minus 2 times 3x minus 2. Distribute the 5. By and like terms. So then we would take a look at this domain, which is also a polynomial function, all real numbers. And then we would intersect that with this domain. Well, if they're both all real numbers, it's not that interesting. We just get a domain of all real numbers from negative infinity to positive infinity. Find g composed with f of x and its domain. So this time the inner function, the second one listed is f. We will start there, that being our inner function, and we need to identify its domain, which we've already talked about a couple times here, bracket 0, infinity. Then let's do the composition. That gets plugged in here. So we're going to replace the x with the square root of x. its domain is actually the same thing, and then when we intersect them, if they're both the same, then that is our domain from 0 to infinity. Part C, f of x, g of x, f composed with g of x. I think we might see something a little bit different this time, as both the previous ones, the two domains that we care about have been the same, so not really all that interesting. But let's go through g being our inner function. What is its domain? We talked about this before when this was the square root of 4 minus x squared. So this being the same kind of process, we could go through that or just kind of extend our knowledge from there and say, hey, that's got to be from negative 3 to 3. Bracket negative 3 comma 3. All right, so now let's do f of g of x. So we're going to take our inner function and plug it in there, substitute there. So we need to square this. 9 minus x squared minus 9. And we get negative x squared. So the domain for that, as it's just a parabola that's been reflected, is all real numbers. But now, the domain for the composite function is that domain overlapped with this domain. So right there, that's the restriction right there. That's our domain. Okay, checkpoint. Go ahead and find h composed with g of x and its domain. Pause the video here. Come back when you're ready. So g of x being our inner function, its domain, clearly bracket 0 comma infinity. We substitute that in here, 1 over the square root of x being squared. We get 1 over x as the function. The domain there for that part is x cannot be 0. So we would then overlap or combine those two domains. So we're talking about here, but can't be 0, so we're going to remove the 0 with the parenthesis, and that's the domain for our composed function. Example number 7, reversing that, decomposing a function. So given the final answer, essentially, can we come up with two functions f and g such that when we compose them, we get this? And there's usually multiple correct answers that we can go with. So what should we want to start with the inner function. So what would be the inner function? Something that's mathematically is happening to, well, in this case, we're taking the square root of something. So our inner function could be what we're taking the square root of. So that could be 9 minus x. And then what's happening to the 9 minus x? It's being square rooted. So that could be our function. Take the square root of the input. Since our input's x, we're talking about the square root of x. F of x would be the square root of x. There's other more complicated ones that we could come up with, but that's kind of the most basic one that we could use. All right, and then we're going to finish with the example square root 30, as this is going to help on some of the homework. And then it's talk about whether we're talking about, and there could be another graph as well, f of 3 plus g of 3. Well, in order to do that, we need to be able to figure out what is f of 3. And we don't need to come up with the algebraic representation of what the function is. We could just use the graph to be able to figure it out. So f of 3, usually this would be f of x. So 3 has taken the place of the x. So we want to go to the graph where 3 is the x coordinate. And that would be here. And f of 3 means what's the y coordinate, the output, at that place? It's going to be 4. Let's try again. What about f of 4? Same thing, go to an x-coordinate of 4 on the graph. We want to know the y-coordinate. It is 2. And we might use this to be able to answer something like f composed with f of x. Yes, you can compose a function with itself. So that just means f of 3. We just found out that f of 3 is 4, so this becomes f of 4. And we also know that f of 4 is 2, so 2 is the answer just by using the graph. That's it for today. I'll see you next time.